Okay, basically we're going to look at examples of variation of parameters. And again, we're going to have the caveat that this is a little bit different than what you normally see or what's in the book or what you normally see online, in that it's a little more general and we're not looking at a special case. So in this example, we have y double prime plus y is tangent of t. So the first thing to recognize is it's constant coefficient, it's first order. We can solve the homogeneous equation, but I have no idea what to guess for the right-hand side. I don't know what function, when I take derivatives of it and work with the original function, I'm going to get tangent. So for that reason, I'm going to use variation of parameters. One of the most important parts about doing this is looking at the equation and just figuring out your plan of attack. So now, in the examples that follow, I'm just going to assume you can get the homogeneous solution and not spend time on it, but I'm going to do it in this first case just to go through and show you the whole process. So the first step is get the homogeneous solution. And so for the homogeneous solution, we have y double prime plus y is 0. Again, it's constant coefficient, it's linear, so I'm going to assume an exponential function. I'm going to take derivatives. And I'm going to plug those derivatives into my homogeneous equation. So the second derivative is c e to the nt times n squared. The function is c e to the nt, and that has to equal 0. And my solution can be factored out, which leaves me is that c e to the nt times n squared plus 1 equals 0. I don't want that to be 0 because that means my solution, homogeneous solution is 0, and that's not helpful. So that means n squared plus 1 is 0. N squared is minus 1. So n is going to be the square root of minus 1 plus or minus. So it's either I or minus I. I can think of this as 0 plus I or 0 minus I. So the real part is 0. The imaginary part is 1. I should say plus or minus 1. So that means my homogeneous solution is going to be e to the 0 t times c1 cosine t plus c2 sine of t. And I can clean it up. E to the 0 t is 1. So I'm just left with c1 cosine t plus c2 sine of t. All right, so, and now I want to do my particular solution. And we've already decided we're going to use variation of parameters. So my particular solution now is going to be v1, some function of t. I'm going to just let u1 be cosine of t, because that's this homogeneous solution, plus v2 times the other one, which is sine of t. And again, I've got two unknowns. I'm going to plug this into my original equation. And when I do that, I'm only going to have one equation, so I'm going to make something up on the way and see how it goes. So what do we have? Again, we have y double prime plus y is tangent of t. I've got a particular solution that looks like v1 cosine of t plus v2 sine of t. Now when I take derivatives, I got to use the product rule. So I'm going to have v1 prime. I'm going to drop the of t here just because I'm lazy. So derivative of v1 times cosine of t. Then I'm going to have v1, derivative of sine is minus sine of t, and plus derivative of v2 times sine of t, and then derivative of sine is going to be plus cosine of t. Now, if I'm going to take another derivative of this, I'm going to end up with second derivatives of v1 and v2, and I don't like that. So I'm just going to arbitrarily say I'm going to let anything with one derivative in that term, which is going to be that first term plus this term, I'm just going to say let that be 0. because I could let it be anything I want. This is just the easiest, nicest thing. So then my y prime becomes minus v1 sine of t plus v2 cosine of t. So now when I take the second derivative, I use the product rule again. So I'm going to get minus v1 prime sine of t minus v1 cosine of t. Then for the v2 cosine of t, I'm going to get v2 prime cosine of t. v2 derivative of cosine is minus sine of t. So plugging this into the differential equation, I have the first derivative, minus v1 prime sine of t minus v1 cosine of t plus v2 prime cosine of t minus v2 sine of t plus y, and that's going to be this thing here. That's plus v1 cos t plus v2 sine of t, which is coming from this line. That all has to equal tangent of t. And at this point, a lot of things should drop out. If they don't drop out, you did something wrong. Notice those two terms cancel, and I'm left with 0. Those two terms cancel, and I'm left with 0. And so this equation becomes minus v1 prime sine of t plus v2 prime cosine of t is tangent of t. That's my first equation. This thing v2 prime sine of t is 0 is my second equation. I now have two equations, two unknowns, and note it's only v1 prime and v2 prime everywhere. If you get anything that is like v1 or the second derivative of v1, same with v2, if that shows up here, again, you've done something wrong. So what I'm going to do now is I'm going to use this to solve for v2. That'll give me something for v1 or v2 that I can plug into here, and I'll only have v1 to mess with. So from this equation, if I subtract the v1 prime from both sides, I get v2 prime sine of t is minus v1 prime cosine of t, and v2 prime becomes minus v1 prime cosine over sine. So taking that and plugging it into the first equation, I get minus v1 prime sine of t plus a negative v1 prime cosine over sine is, oops, I gotta be careful, times cosine equals tangent. Is that correct? So that's that term. All of this times cosine, I think we're okay. I don't like that sine. Let me multiply everything by sine of t. If I do that, I get a minus v1 prime sine squared. Make that a minus v1 prime. Though that sine's going to drop away, I'm going to get a cosine squared. And I'm going to get sine of t times tangent. I'm going to write sine of t as sine over cosine. And yeah, I think we're okay. Okay, so now I can factor out a v1 prime and a negative sign. I'm going to get sine squared plus cosine squared equals sine squared over cosine. Sine squared plus cosine squared is 1. Put the negative on the other side, I get v1 prime is minus sine squared times cosine. So I just got to do an integral now. All right, so let's, what do we have? We have our differential equation is y double prime plus y is tangent. We said that our solution is v1 cosine t plus v2 sine of t. And we had that v2 prime is minus v1 prime times cosine t over sine of t. And we just figured out that v1 prime is minus sine squared times cosine of t. So I can plug that straight into here, which means that this thing becomes minus a minus sine squared over cosine times cosine over sine from this term. Minus minus cancels. And I am left with the cosines cancel. This just becomes sine of t. And I think I like that. Okay. Sorry, just checking my work, and that's what I had before. Okay. All right. Let's do the V2 first. That's the easier one. So I have V2 prime is sine of t. So if I take the integral of both sides, with respect to t, antiderivative of v2 prime is v2, antiderivative of sine is minus cosine, but then I'm going to have a plus k1 is my constant. So there's v2. Now for v1, now this is going to be a mess. So I'm integrating trig functions, so I'm going to have to do trig identity nonsense. But the process is exactly the same. I take the antiderivative of both sides. Antiderivative of v1 prime is v1. Let me pull the negative sign out. Sine squared is what? 1 minus cosine squared? And I'm doing that to get everything in terms of cosines, and I'm not going to do a u substitution because derivative of cosine is going to be sine, and I've got a sine squared. So let me try this. If this doesn't work, I'll just try something else. Let me break this up into two pieces. I get 1 over cosine t minus cosine squared over cosine. So this is the integral of the secant minus, and then cosine squared over cosine is just cosine, and I'm in luck, I can do that. Right. So from Calc 2, this becomes minus the log of secant plus tangent, and the antiderivative, I gotta be careful here, minus all of this. Antiderivative of cosine is what? Sine. And I just did an antiderivative, so I'm going to have a plus k2. So let me pull that minus through. I get minus log secant of t plus tangent of t plus sine of t plus k2. So this is my v1. I've got my v2, and now I can plug into here. And so what do I get? I'm going to get now that my particular solution is v1, which is minus log secant t plus tangent of t plus sine of t plus k1 all times cosine of t plus, now for my v2 is minus cosine of t plus k1. Oops, be careful. This k2 here. This has a k2. It's k1 and times sine of t. So let's expand that out. So I had minus log of secant t plus tangent of t. Oops. Let me rewrite that. yp becomes minus log of secant of t plus tan t plus sine of t plus k2 cosine of t plus the quantity minus cosine of t plus k1 times sine of t. And now the reason I'm expanding all this out is I want to show something important, is that now I'm going to have minus log of secant of t plus tangent of t times cosine of t plus sine of t cosine of t plus k2 cosine of t. So that goes that term, that term, that term. And now here I'm going to have minus cosine of t, sine of t, plus k1 sine of t. Notice those two things cancel out, and I'm just left with this term plus these terms, but these two are my homogeneous solution. So I actually don't have to come back and add it because it's already in there. And if you do everything correctly at the very end, your homogeneous solution should be in there. And it should get picked up because of the constants of integration. So that should be in your solution. If it's not, you did something wrong. Okay, let me do one more example. All right, so for the second example, and this will be the last example for the day, I'm going to have y double prime plus 3y prime plus 2y is 1 over 1 plus e to the 2t. It's constant coefficient. It's second order and is linear, so I know how to find the homogeneous solution. I don't know what to guess for that. That's an awful mess. Right? I don't have any idea what kind of function I can take derivatives of and end up with that. So for that reason, I'm going to use variation of parameters. All right, so first step is to get the homogeneous solution. So for the homogeneous solution, I have yh double prime plus 3yh prime plus 2yh is 0. It's constant coefficient, it's linear. So I assume an exponential. I'm going to take derivatives, so I get the exponential times r. For the first derivative, for the second derivative, I get c e to the rt times r squared. And I plug it in. Second derivative is c e to the rt r squared plus 3 times the first derivative is c e to the rt times r plus 2 times the original equation is 2 times c e to the rt is 0. E to the rt, e to the rt, c e to the rt. So I can factor out c e to the rt. Left with r squared plus 3r plus 2. I don't want that to be 0 because that means my homogeneous solution is 0. So I get r squared plus 3r plus 2 is 0. I can factor that. So r is minus 2 and minus 1. So my homogeneous solution is c1 e to the minus 2t plus c2 e to the minus t. Now for my particular solution, and again, I don't know what to guess, so I'm going to use variation of parameters. So for my particular, I'm going to have some unknown v1 times my first thing plus some unknown v2 times my second homogeneous solution. And both v1 and v2 are functions of time. I'm going to plug this into my original DE and see what that means. So I got to take two derivatives. I have two unknowns. I only have one equation, so I'm going to make something up after this next step. So my first derivative is going to be v1 prime times e to the minus 2t plus v1 times the derivative of e to the minus 2, which is e to the minus 2 times minus 2. And let's do this plus derivative of v2 e to the minus t is v2 prime e to the minus 2 plus v2 e to the minus t times a minus 1 because the derivative of minus t. That right there, anything with a derivative in it, I'm just going to say adds up to 0. So I'm going to get v1 prime e to the minus 2t plus v2 prime e to the minus t is 0, which leaves me with yp prime is minus 2 v1 e to the minus 2t, minus v2 e to the minus 2. So now I'm going to take the second derivative of that so I can plug it in. So what do I have? I have my original differential equation. It's y double prime plus 3y prime plus 2y is 1 over 1 plus e to the 2t. My homogeneous solution was c1 e to the minus 2t plus c2 e to the minus t. Okay. My particular solution was v1 e to the minus 2t plus v2 e to the minus t, and that led us to the derivative being yp prime is minus 2 v1 e to the minus 2t v1 minus v2 e to the minus t, but that's only true if v1 prime e to the minus 2t plus v2 prime e to the minus t is 0. So that's my equation 2. So now when I take the second derivative, I'm going to have minus 2 v1 prime, because I have to use the product rule on the first term. So I'm going to have minus 2 v1, derivative of e to the minus 2t is e to the minus 2t times minus 2. Oops, it's going to be minus v2 prime e to the minus 2 minus v2, derivative of e to the minus t is e to the minus t times a minus 1, so that becomes a plus. So now I'm going to take this and plug into my differential equation. So I get y double prime is minus 2 v1 prime e to the minus 2t minus 2 v1, minus 2 times minus 2 is plus 4 v1 e to the minus 2t minus v2 prime e to the minus t plus v2 e to the minus t plus 3 times y prime is this term, so I get minus 2 v1 e to the minus 2t minus v2 e to the minus t plus 2 times y, and that's going to be c1 e to the minus 2t plus c2 e to the minus t, all that equals 1 over 1 plus e to the 2t. That's a 2. I'm getting sloppy. So let's multiply all that out. So I'm going to get minus 2 v1 prime e to the minus 2t plus 4 v1 e to the minus 2t minus v2 prime e to the minus t plus v2 e to the minus t. 3 times the minus 2 gives me minus 6 v1 e to the minus 2t minus 3 v2 e to the minus t. And multiplying that through by 2, I get plus 2 v1 e to the minus 2t plus 2, that should be, I should have been using this, sorry. This should be v1 and v2 plus 2 v2 plus 2 e to the minus t all equals 1 over 1 plus e to the 2t. Anything that does not have a derivative should cancel out here. If it does not, you did something wrong, because this is a homogeneous solution. These all add up. 4 minus 6 plus 2 is 0. 1 minus 3 plus 2 is 0. So that just leaves me with my second equation, which is minus 2 v1 prime e to the minus 2t minus v2 prime e to the minus t is 1 over 1 plus e to the 2t. So these are my two equations, two unknowns. So this is my equation 1. This is my equation 2. So let's write all that down again. So we assumed a particular solution looked like v1 e to the minus 2t plus v2 e to the minus t. We plugged that into the equation and asked what it implies, and we got two equations. We got minus 2 v1 prime e to the minus 2t minus v2 prime e to the minus t equals 1 over 1 plus e to the 2t. And the other equation is v1 prime e to the minus 2t plus v2 prime e to the minus t is 0. These are my two equations, two unknowns. I am going to solve the second equation for v2 prime and plug it into the first equation. So v2 prime e to the minus t is minus v1 prime e to the minus 2t. By the way, we're seeing now why that 0 is so nice. multiply both sides by e to the t, so I get v2 prime is minus v1 prime e to the minus t. Plug that into the first equation. Let me be careful here. I need to keep track of that. I'm going to use that. I have minus 2 v1 prime e to the minus 2t minus v2 prime, which is minus v1 prime e to the minus t times e to the minus t. It's 1 over 1 plus e to the 2t. So let's clean that up. Minus 2 v1 prime e to the minus 2t plus v1 prime, and this becomes e to the minus 2t, 1 plus e to the 2t, minus 2 of these plus 1 of these becomes minus v1 prime e to the minus 2t. So 1 over 1 plus e to the 2t. Multiplying by minus e to the 2t, I get v1 prime is minus e to the 2t over 1 plus e to the 2t. So that's one equation. I got to just integrate both sides for that. Coming back to here, v2 prime is going to be minus v1 prime, which is minus a minus e to the 2t over 1 plus e to the 2t times e to the minus t. So I get v2 prime is e to the t over 1 plus e to the 2t. So those are my equations for v1 and v2. So v1 is going to be the antiderivative of minus e to the 2t over 1 plus e to the 2t dt. And v2 is going to be the antiderivative. Okay, it's going to be positive. Does that make sense? There should be a negative. Yes. E to the t over 1 plus e to the 2t dt. So where are we now? We have y particular is v1 e to the minus 2t plus v2 e to the t. v1 is negative antiderivative e to the 2t over 1 plus e to the 2t dt. And v2 is the antiderivative of e to the t over 1 plus e to the 2t dt. I think this one's easier because I see a derivative of e to the tt hanging out. So let's do this. v1 is negative e to the 2t over 1 plus e to the 2t dt. Let's do a u substitution. We'll let u equal e to the 2t. So du is 2 e to the 2t dt. So this becomes negative 1/2 of 1 over 1 plus u du. So I get minus 1/2 log of 1 plus u plus k1. So this becomes minus 1/2 log 1 plus e to the 2t plus k1. So there's my v1. v2 is the antiderivative of e to the t over 1 plus e to the 2t. Now, look, so e to the 2t I can write as 1 plus e to the t squared. And there's the derivative of e to the t. So if I let u equal e to the t, du is e to the t dt. This becomes 1 over 1 plus u squared du, which is the arctangent of u plus k2. So this is the arctangent of e to the t plus k2. And that's my v2. So coming back to here, yp is v1. Where's my v1? It's minus 1/2 log of 1 plus e to the 2t plus k1 times e to the minus 2t plus v2, which is that horrible looking thing, arctangent of e to the t plus k2, oops, that should be an e to the minus t, times e to the minus t. And there is my solution. And notice when I multiply this through, k1 times that is my homogeneous solution, and k2 times e to the minus t is my other homogeneous solution. So this looks like a particular plus a homogeneous, so life is good.